Welcome back to the examples of shear force diagram and the bending moment diagram. We have already explored the first example with a central concentrated load on a beam. Now it is time that we look to the second example. It is a simply supported beam with a uniformly distributed load over its entire length. So as you understand, it is easy for you to, this is the intensity of load. So total load will be omega L and the reactions will be omega L by 2 and omega L by 2. So the free body diagram will consist of the active load and the reactions. I'm not going to explain how you have to draw this, and you practice it alone. Now, if we are interested to find out the shear force diagram and the bending moment diagram, so as per our understanding, we will take a point on the longitudinal axis and cut a section and separate the beam into two parts, and then examine each of the parts separately, and then try to find out what are the shear forces and the bending moments acting over there on the cross section. Here I have not shown the two parts as I have done in the previous example. You do it yourself. What I have forgotten here is to indicate the Vx and Mx, but I have written them, but here I have forgotten it. So the right part, right down shear here, and an anti-clockwise moment should have been there. So with that, this part will be in equilibrium. So if this part in equilibrium, if this write down, you can assume if it is the right part, so it is omega L by 2 minus this should have been equated to that shear force Vx. So it is omega L by 2 minus omega into x is the total force over the length x, and that should be equated to Vx here at the cross section, which I have not shown. You just draw it. And mx similarly, which is on the right part, so it is an anti-clockwise moment. So it will be omega L by x will create a counterbalancing moment to that, and omega x into x by 2, the distance from the section, the distance of the CG of this loading from the section is x by 2, is x by 2 here, is x is here, and x by 2 is here. Now mx is omega L by 2 into x minus omega x into x by 2, and that's equal to the mx working counterclockwise. So you get the equation of Vx and Mx. Now you put the values of x equal to the salient features, and unlike the previous problem, there is no concentrated type of load which changes the characteristics of the beam. So we can take a single section, we can afford to take a single section and extend it from the left end to the right end. So you put x equal to 0, you get the shear force omega L by 2, it is positive shear, and you put x equal to L by 2, you will find shear force is 0, and if you put x equal to L, you will find the shear force is negative omega L by 2. So this expresses the shear force diagram. And then if you put x equal to 0, L by 2 and L, you will find that both sides is 0. The variation is parabolic from this equation omega x square by 2, and you will have the moment omega L square by 8 maximum in the middle. So you can also find out the maximum value of mx by, as you find out in any function, the maxima and minima, you get dmx dx is equal to 0, you do it and you will get where it is maximum, you will get it L by 2. So this explains the shear force diagram and the bending moment diagram of a simply supported beam with uniformly distributed load over its entire length. Now let us explore a few more problems quickly. So this is a simply supported beam with a concentrated moment in the middle. You see, I have explained the first problem very elaborately, the next problem less elaborately. Now I am explaining further less, and after that I will show you the answers and you have to do it yourself. So if a concentrated couple or moment acts in the middle of a beam, you can see this M moment is clockwise. So the reactions at the left end and the right end, since it is a hinge joint at the left end and a roller joint at the right end, there is no horizontal force or vertical force. It's just a couple of applied here in the center. So there will be equilibrating forces vertically up or down. Now whether the reactions are up and down, you can easily find out because M which is trying to rotate the beam clockwise, the reaction should try to rotate the beam anti-clockwise. So the reaction should be moment divided by the total length m by L, and the left end it will be m by L, and right end it will be m by L up. If you have any confusion, you find the couple m by L into L is the couple which is the m. So you got the reactions. Now you know what to do. You pass a section at a distance x, and then look at your left. This is left down. You have assumed left up shear positive. So definitely you will have a negative shear downward of magnitude m by L. And as you pass from here to here, you don't encounter any other forces but a moment. So the shear force diagram will be constant throughout. If you have any confusion, you come from the right side. You have assumed left up, right down. Again, right up. So it is a negative shear from the right. M by L, negative shear. So M by L, negative shear from the left. M by L, negative shear from the right. You have a complete M by L negative shear force diagram throughout its length. So now for the bending moment, you consider a section at a distance x. Those things you have to do in the examination. I am not doing here for explanation. So it is m by L into x. And now the bending moment in the middle will be actually m by L into L by 2, m by 2. So up to here, and your bending moment convention, it is, if you consider the left part, your anti-clockwise moment should have been positive. But now if you sit here at a section, anti-clockwise moment should have been positive. But you see, sorry, that your clockwise moment should have been positive. Now what this particular m by L force tries to do with you, it tries to put it in the anti-clockwise direction. So it is a negative bending moment as per your convention. That is how up to here m by 2 moment it is negative. But the situation changes when you cross this m couple. So if you are here crossing m, what will you see? You will see one moment which is m by L, another moment m. M is obeying your convention. So that is positive. So you will put it m by L into x minus m into this direction. So it will be x minus L by 2. So you will find out that it is actually positive, and you can find out at different sections. Now, if it confuses you, don't worry, you come from the right side. You take a section at a distance x from the right. It is m by L into x from the right, from a section here, so towards the right. Now you see what this guy wants to do with you, m by L. But as per your convention, if you consider the right part, the anti-clockwise moment is positive, and you are happy to observe that this m by L creates a positive moment. You see, then m by L up to L by 2, that is m by 2, it will be positively increasing from 0 to m by 2. So this is actually the moment diagram. Once again, I should not have joined by this vertical line, but I have joined to actually a handy diagram for you, but you no need to join these. So it is m by 2 positive moment from right side gradually increasing from 0, and m by 2 negative moment gradually increasing from 0. Again, you observe that with a concentrated moment, the location where the concentrated moment is actually applied, the bending moment jumped from the m by 2 to add minus m by 2 to add another m to it to become plus m by 2. So for a concentrated couple, the bending moment actually changes abruptly and the shear force remains constant. Whereas you can find out from our previous example that for a concentrated force, the shear force abruptly changes, and the bending moment you have to find out whether there is no abrupt change between these points. Now we will learn it further later. Now I can add one more example quickly, that if you have understood very well the simply supported beam, why not to consider a cantilever beam and explore that how the bending moment and shear force diagrams will look like? Take an example of a cantilever beam with a tip vertical downward force P here. If that is so, then you have a P force here. So the reaction at the left end, where it is the only support for the cantilever beam, you should have definitely equilibrium force P to counteract this P force. And also the P force, it creates a moment of P by L. Actually, it is clockwise. So the reaction should be anti-clockwise PL. So it is PL clockwise, PL anti-clockwise, not P by L, sorry, PL. So if you can complete the FBD, free body diagram of the cantilever beam with the applied tip force P, then you have to carefully examine by considering at a distance x either from the left or from the right. For this particular cantilever beam, it is always, mostly, it is always convenient to take the section from the free end. So if you consider a section at a distance x and carefully examine the shear forces, you have assumed left up, right down. You are here at a section, you are seeing a right down force, so you have a positive shear force. And that does not change. As you go here and look towards your right, you always see a force P as a shear force which is downward. So right down is a positive shear force here, and this is the shear force diagram. Now, how about the bending moment diagram? If you consider at a distance x, you have a p into x moment at the section working. But how it is? You have assumed with your sign convention an anti-clockwise moment positive, but this p into x is creating a clockwise moment, so this is negative. You see, this is a negative moment. And it increases as the x is increased from right side to engulf up to L. You have a total moment p by L, which is negative. You see, is P by PL, sorry, PL is the moment at the left end gradually increasing negatively. And this is the bending moment diagram for a cantilever beam with a tip load. Similarly, you can explore instead of a tip load if you have a concentrated moment applied at the cantilever beam. I say this is practically very, very difficult, but theoretically, for completeness, we put forward this nice example to explain to you the shear force and bending moment diagram. If you have only a concentrated moment here, your reactive moment will be only a moment here and there is no force acting. So if you take a section at X and observe anywhere, you will not see any force and your shear force is zero. If you consider at anywhere at a distance x, and if you look to your left and right, you see your left part, your clockwise, and right part anti-clockwise. The moments are positive in your sense, and you have a positive constant bending moment diagram. This is the BMD. This is the SFD 0, and BMD is here. So this next example I am not going to explain to you, you do it yourself. So I have applied a concentrated force onto the simply supported beam and a concentrated moment onto the simply supported beam at a different location. You find out from your statics principle the reactions. You will find it is 3.75 kilonewton on the left end and 3.25 kilonewton on the right end. So you have a force and the couple acting at two different points. So if you are interested to find out the bending moment, you pass sections here, sections here, section here, and divide the beam into two parts at a time, and then examine carefully the equilibrium equations. And similarly, what you have done earlier, you can draw the bending moment and shear force diagram. I can give you the observation now here. The shear force, as it is left up, it is positive 3.75 shear, and then 7 load will put it down by 7, and 3.75 minus 7 is actually minus 3.25. And then henceforth you don't have any force and you go rightwards straightway with a negative shear. If you still do not understand, you examine the right side, you have a left up, right down positive shear. So 3.25 right up shear is negative, and you have a 3.25 negative shear. Mind that when you have a concentrated force, the shear force changed abruptly. Coming to the moment diagram, you will similarly have 3.75 into x, and x varies from 0 to 2 meter. Ultimately, you will have 7.5 this thing. And then the bending moment diagram drops down, and you will find wherever you have applied a concentrated moment, the bending moment diagram simply shoots up. And since it is here, it is a clockwise moment, it will add up to it. If you are in any confusion, come from the right side. 3.25 into 4 is the bending moment value here. So it is 13. And then it should drop down immediately because you have a bending moment here, which according to you is still it is just counteracting to the 13 bending moment, and you have a 1 kilonewton bending moment. The 12 is deducted from 13. You do it yourself, try it, and it's a very nice example to show you the effect of concentrated force and a concentrated couple together. Let us stop it and we'll continue further into through the next example.